A uniform cylinder has a radius r and a length L. If the moment of inertia of this cylinder about an axis passing through its center and normal to its circular face is equal to the moment of inertia of the same cylinder about an axis passing through its center and perpendicular to its length. Okay, so first look at this. Okay, we have a uniform cylinder. Okay, there is this axis passing through the center of this and perpendicular to one of its faces. Okay, and normal to its circular face. Okay, so what is this moment of inertia? This is a solid cylinder, so I is equal to mr square by 2. This is the moment of inertia, we know already this. Okay, now this moment of inertia is equal to the same cylinder about an axis passing through its center and perpendicular to its length. That means this moment of inertia. Let's say this is I dash. Now what is this moment of inertia? How will you find that moment of inertia? So here we cannot use parallel axis, perpendicular axis theorem, because cylinder is not a planar body. We cannot use. Then what we can do? What we can do is we can take this as a cylinder like this. Okay, and draw an axis passing through its center like this. Let's say this is the I. Okay, I dash, basically I dash. Okay, now what we can do, this is a solid cylinder, right? So this is having length L and radius R. We have to find out its moment of inertia. Now how will you find the moment of inertia of this? See, what we can do is we can take, let me use different color. Okay, let's use a disc here. Okay, let's say there is a disc. Okay, let's say it has a thickness of dx. It has a thickness of dx. It has a thickness of dx and radius will be r. Okay, now we have to find out the moment of inertia about this axis because of this disc. How will you find that? You can see that all the mass is at a distance x. Let's say this distance is x. This distance is x. Okay, the disc is at a distance x from this center. So now what is the mass of this disc? Let's say it is dm. Dm is the mass of this disc, right? And the cylinder is a uniformly distributed mass. So rho is equal to m upon pi r square into L. This is mass per unit volume. So that is rho. Now dm by dv can be written as rho. So dm is equal to rho times dv. dm is equal to rho times dv. Okay, so rho is a constant. Rho is a constant. So what is the dv? dv is the volume of this disc. Volume of this disc. So pi r square dx. So rho into pi r square dx is the dm. So dm will be equal to, rho is m upon pi r square L. So this will be m upon pi r square L into pi r square dx. This pi r square will get cancelled with this. We have m by L dx. This is our dm. Okay, this is our dm. Now this dm is at a distance x from the axis, right? So now we will find out the moment of inertia because of this mass here. Now how will you find the moment of inertia of this disc about this axis? Now one thing we can say is that the moment of inertia, this is a body like this and there is this axis passing through the center of this disc, okay, passing through the center. Now we know this is mr square by 2. The moment of inertia of this disc about this axis is mr square by 2. So about this axis it will be mr square by 4, but the mass is dm. So it is dm r square by 4. dm r square by 4. Now this is axis passing through center of mass. Now if we use parallel axis theorem, then I can say This is dm r square by 4 plus dm into x square, right? So di is equal to dm r square by 4 plus dm r square by 4, this about this x is the moment of inertia, plus dm into x square, dm into x square. This is the moment of inertia. So now let's integrate this. Okay, what will happen if we integrate? So this is integral over di. Now integral over dm will be simply m, because r is a constant, right? R is a constant, and dm is equal to m by l dx. So this is x square. So we have to integrate over this. So we will integrate x with the to 0 to L, and dm is over a total mass. So let's find out what is this moment of inertia. So I is equal to integral dm is m. So this is mr square by 4 plus m by L x square dx. Now x square dx is x cube by 3, right? X cube by 3. So m by L into x cube by 3. Okay, the integral is from 0 to L. So the limits are from L to 0. Actually, it is from L by 2 or 0 to L by 2. See, we will take 0 to, not 0 to L, it is 0 to L by 2. We are going from 0 to L by 2, right? Only half distance. So we have to consider this also. So then we will multiply by 2. We will multiply by 2. Extra 2 factor will be there. Okay. So this will be 0 to L by 2, and 2 factor we missed, right? So this is here, 2 factor. So this is mr square by 4 plus 2m by L. This is L cube by 24, because 2 to the power 3 is 8. 8 3s are 24. So L cube by 24 minus 0. Okay. So now this will be mr square by 4 plus m L square by 12. This is the moment of inertia. Okay, that one. That is I dash. This is I dash. Okay, this is I dash, that is this. Now what is given to us? This I dash is equal to this. I is mr square by 2. So I dash is equal to mr square by 2. So this is equal to mr square by 2. So mr square by 2 is equal to mr square by 4 plus ml square by 12. So if I multiply by 2 both sides, we will get mr square by 4 here is equal to ml square by 12. M cancels, 4 into 3. So if we take a square root, r is equal to plus or minus L by root 3. R is equal to plus or minus L by root 3. L by root 3. Okay, so L is equal to root 3 R. L is equal to root 3 R. L is equal to root 3 R plus or minus root 3 R. So L is equal to root 3 R is correct option. That is this one.